Alright, so again, if you have increased heart, so we'll talk about hemoglobin. So hemoglobin, again, that protein you find in red blood cells. So what happens when you increase partial pressure? Well, you increase the oxygen binding to this special on protein called hemoglobin. So then you have something called oxyhemoglobin. So I'll be using this abbreviation a lot in this lecture. So hemoglobin will be abbreviated as HB. So HbO2, this is when you have oxygen bound to hemoglobin. So what happens when you have oxyhemoglobin saturation? So again, or how do you calculate it? So it's basically how much of your hemoglobin is actually bound to oxygen. So 100% saturation means that the HbO2 is equal to all the hemoglobin in your body. So 100% means that all the hemoglobin in your body and all the heme in the hemoglobin has oxygen bound to it. So increasing partial pressure past this point has no real effect. Why? Because like all the hemoglobin is totally full with oxygen, so it's at capacity. And so this is what we have with the saturation curve. So you'll see this in the book, and this is one of those things like physiologists, they love graphs, and they're very abstract at first, but they also have a lot of information if you look at them and break them down bit by bit. So let's look at this part right here. Let's look at that table. So what do we notice? So here we have the partial pressure of oxygen at different partial, again, less partial pressure, fewer oxygen molecules. So what happens when you increase the partial pressure of oxygen inside your blood? Well, notice that as you increase the oxygen partial pressure, you also increase the amount of hemoglobin that actually has oxygen bound to it. So more partial pressure of oxygen, more formation of oxyhemoglobin. So what we have here, again, the more you increase the pressure, the more oxygen that ends up sticking to hemoglobin inside of red blood cells. So if you keep on increasing the pressure, you get more and more oxygen binding to hemoglobin. And at a certain point, so what do you see? You see more and more oxygen molecules binding and sticking to hemoglobin. But at this part right here, once it gets around the 80%, or actually not 80%, partial pressure around 80 millimeters mercury, start to see that it starts to reach its capacity. So this is why it doesn't start keeping going up and up and up. Around this point, it starts to slow. So you can increase the partial pressure more and more, but at a certain point, you reach around 100%, and even if you increase partial pressure past this point, it's only going to increase it maybe by 1 and 2%, versus down here, where there was low oxygen partial pressure, even a difference of 20 millimeters mercury caused a huge jump in the oxyhemoglobin saturation. So hemoglobin and oxygen. So again, remember, hemoglobin is actually it is a protein, but there are 4 polypeptides in it, and also there are 4 heme molecules. Again, that heme is actually what binds to oxygen. These little discs right here and this little red dot is supposed to represent iron. So that central iron in a heme molecule, that's where actually oxygen specifically binds to. But the thing about oxygen binding to heme, once it binds, does it just stuck there? No, it can actually pop on and off. So this oxygen binding is reversible. Again, when you're breathing in air from your environment into your lungs, so once you go, the oxygen moves from the alveoli into the blood. Yeah, you do want oxygen binding to heme so that it's able to hang on when it's being transported in your blood, and then you want it to pop off when it's actually on the tissue, at your tissues. So if it's reversible, how do you get oxygen to stay bound to hemoglobin in the alveoli? Well, again, remember things move from high to low, right? So again, partial pressure of oxygen entering pulmonary capillaries around 40. So just by that diffusion and again that pressure difference, but since you always have a higher concentration of oxygen in the alveoli, you're always going to get this movement of oxygen into the blood entering your pulmonary capillaries. So this helps to keep oxygen stuck to hemoglobin. So again, at alveolar partial pressure, you have almost 98% of the hemoglobin stuck to or bound bound with oxygen. So it's the higher alveolar partial pressure that keeps oxygen bound to hemoglobin in your alveoli. How does that? Ooh, actually, that's a good question. I'll stop right here for that. So the pulse oximeter, that's what we call, and actually, what do I have my phone here? Like, I don't have an iPhone with me right now, but this is like a old Samsung, don't judge. But actually, it has these little lights right here, and I think the Samsung S Health, you can actually check what your oxygen saturation in your blood. So what it does is actually shine a light, and then this light is actually somehow, so some of it is absorbed by the color of your blood. So the fun thing about deoxygenated blood is actually, okay, so common misconception, deoxygenated blood is not blue, but it is slightly darker. So by measuring the amount of light that's reflected, so it can shine light and see how much light is actually reflected and absorbed by that darker blood, or again, conversely, oxygenated blood is brighter. So by measuring the color of the blood the light that's reflected, it can actually determine how much the ratio of oxygenated blood to deoxygenated blood. So it's really cool. It just uses light. So how does oxygen stay? Okay, so hemoglobin. So again, hemoglobin is a protein, not a cell. Hemoglobin is inside your red blood cells, but again, it's not a cell, it's a protein. So how does hemoglobin know when to unload oxygen into tissues? Alright, so again, once it enters you do lose about 5 millimeters mercury of oxygen as you go from your lungs and when it finally makes its way to your tissues. So remember, partial pressure of oxygen in your interstitial fluid is around 40. So which way is it going to move? High to low, right? So this is how you're able to unload oxygen, just by the difference in partial pressure. This will eventually, again, add more oxygen to your interstitial fluid, and your cells are going to take that oxygen. So this is why the partial pressure of oxygen in your interstitial fluid is lower than in your blood. You always have the cells sucking up some of that oxygen, thereby lowering the partial pressure of oxygen. So what do you notice as you move from artery to vein side? Well, again, it's still high to low, right? So you still, at this point, you do lose some oxygen compared to when it first entered the capillaries. So again, your cells are always going to absorb the oxygen, so the partial pressure, as you go from artery to vein side, it starts dropping. Why? It's going into the interstitial fluid, your cells are taking up the oxygen. This is why you lose that oxygen and how you offload oxygen from your blood into your tissues. Yes, that's correct. So hemoglobin itself stays in the blood, but the oxygen is just released. So that's what's popping off. And it's due to the differences in pressure. So I know it's very mathy, and some of you are kind of scared of numbers, but this explains why again, hemoglobin is a protein, so how does it know? It doesn't really know. It's due to the differences in pressure. Okay, so again, constant absorption of oxygen keeps the interstitial partial pressure of oxygen low. Again, pressure moves things from high to low pressure. And there's more things that can do that. Yeah, so I can answer that at the end. So, alright, so the thing is that by lowering partial pressure, now, as we go from this part of that curve, and say we lower the partial pressure, so notice that the saturation will also drop as well. So what happens when the oxygen saturation drops and the pressure drops? Well, as the partial pressure of oxygen drops, this actually causes oxygen molecules to also drop as well. So when you enter a low partial pressure of oxygen environment like interstitial fluid, and the blood that's interfacing with that interstitial fluid, so these oxygen molecules are being released, but where are they being released? they're being released into the environment. So if you're at the tissues, it's releasing oxygen molecules from the inside of these red blood cells and hemoglobin into the environment. So again, pressure differences, this is what it drives how you stick oxygen to hemoglobin, but also how you release oxygen from hemoglobin. So again, lower partial pressure also causes oxygen to pop off from hemoglobin. So hemoglobin and gas exchange,